Hello, folks. This is day number 13 of Advent of Code. I'm Liz the Gray. It's nice to see all of you back again. Hopefully, maybe some new faces. And this is now, I think, the second weekend of Advent of Code. And Eric posted a cryptic warning telling people today that, hey, it's okay to solve it in more than one sitting. So I'm expecting the difficulty to ramp a little bit tonight. Hope everyone's doing all right and kind of holding up okay. I'm doing as well as I can be under the circumstances. I'm a little bit sleepy, but not like completely whack right now yet. So, all right, let's have a look at what we need to do to get this puzzle set up. Feel free to say hi in the chat. Good luck to everyone running today. All right. So 13 input for day 13. Hey, Mukaupong. Long time no see. Hope you're doing okay. All right. Let's see. What do I need to do? Let's go ahead and start my template as usual. Keeping in mind that I have no idea what this is going to be, although we haven't seen a maze search yet this year, so I'm suspecting there might be some kind of tree or graph search. That's what my bet is, but we'll see what it is. Should be exciting. Cool. Let's see. Oh, one thing I did want to mention to folks is yesterday's code. I did want to point out a potential weakness in the code, or at least a thing that people solve differently, which is that this reflection matrix here also can be encoded in terms of polar coordinates, and I didn't actually need trigonometry libraries. All I literally did was multiplying by I, where I is the square root of -1, because there is a mapping between the coordinate plane and the complex number space. So basically, if you think about everything as being ax plus yi, and then you multiply that by I, then you get these transformations that I showed earlier. So that's about the thing I wanted to say that I didn't quite do correctly yesterday, or at least not in a generic manner that would account for rotations of other than 90-degree increments. Cool. So let's just wait for the last minute to elapse. And then we'll see what we have here today. So, plot so far is we got blown off of course, so we need to figure out how we're getting back towards the island. So I think that's what's going on, is we're going to wind up going towards this other island before we wind up winding our way back towards our vacation. So yeah, that should be good. Oh. I have slept, I don't know, slept like 12 hours probably, 12, 13 hours last night, and then I spent a bunch of this afternoon staring at YouTube, doing absolutely nothing, not really capable of doing anything, but it's okay. I'm saving energy to do Advent of Code, and therefore I think that I hope that lying down for most of the day has given me enough energy to do this. All right, let's see what this is. Day 13. Oh no, we need to get back to the airport. Shit. Okay. Yeah. Okay, so this is least common denominators. Okay. Wait, what? So ours timestamp is 9:39. Yep. Those are all multiples. Yep. Flying the bus ID by the. Okay. This is actually a fairly simple divisibility. So we'll just roll with it. Okay. So let's go ahead and give it this. So what do the x's mean? Integers that show x must be out of service, so we ignore them for now. It's probably going to be relevant later. Okay, fine. So, let's see. So the start time is just going to be this first value. All right. Now we need to split this by comma. Ah, there we go. Right. If L is the letter X, then we're just going to skip for now. Otherwise, we need to get the line number. So we want the going to, so soonest is going to be some very large positive number. Let's just call it start time for now. So if line soonest percent line no is less than soonest, or sorry, this is start time, then soonest equals start time percent line no, and now we print out the soonest. Line 24, what's wrong there? Oh, and we just need this error case here as well dealt with, just to make sure we don't have anything weird going on here. Okay. Yep, that's correct. We don't use this I yet, and that's fine. All right. That cannot be right. Oh, because I'm also supposed to, the ID of the earliest bus multiplied by the number. Okay. Okay. And also, number of minutes I'll need to wait for the bus. That seems fine. Wait a second. This is not quite correct. It's not just a percent, because, okay, min to wait is going to be, this is wrong. So I think it's going to be this instead. Okay. Where is line no defined? Really? Is this? Oh, I see. I am now very, very confused. Oh. There we go. Okay. Let us give it this simple input first, just to check it. All right, 295, that's correct. So I think this answer is 2305 here, which is correct. Rank 467, not bad. Okay, cool. 1 gold coin for anyone who can find the earliest timestamp, such as the first bus ID departs at this time, and the subsequent listed bus ID departs at that subsequent minute. Each subsequent bus ID departs at that subsequent... Wait, what?
There are definitely some good projectiles. Like, we fly the Hurricane as one of our documents, so it's like well scaled for that, but...
Oh, I see.
But, yeah, you're definitely on, like, cross-train marks, we use a lot of marbles.
Oh, I see. So I have to get all of these to sequence at once.
That's plus.
What's the... Oh, there are positions in the list. Okay, I am still a little bit confused about parsing this problem. All right. Well, let's start translating some of this into code.
There's like this page that lists our doctrines and make sure you can fly at least one ship for every name that doctrine.
Listed bus IDs at their specific offsets from T. Bus 7 will always be departing with bus 19. Okay. Alright, let's just record these numbers first because I don't want to parse it. Okay. Alright. Let's just deal with this real quickly. Just so I have it, but I'm still very, very confused about what this means. Bus 7 departs at some arbitrary time in the future. Bus 13 must depart 1 minute afterwards. Oh, I see. Okay, got it. Yeah. Okay, now I understand. So we're looking for the following relation to be satisfied. T that wait, that's not quite right. So there has to be T plus 1 is 0, T plus 2 is 0, and so forth. Okay. Now I think I have an understanding of what I'm supposed to do here. Okay. All right. So now they've expressed this in terms of maths that I'm familiar with. Now this feels more reasonable. Okay. So first challenge here is let's have a look at my input. So
yes, it is.
yeah. Okay. I see. So the logical way to approach this is to constraint solve this starting from the highest values. And then after that, I think we can proceed testing the lower values. I think that's probably what makes the most sense. Okay. So this actually. Doesn't really matter which way I do these, I guess. Or does it? I think it does matter. Okay. So. T plus V must be congruent to 0. For each T. For each KV. All right. Now that we've expressed this in terms of the maths, so let's iterate. So how do we approach this? Remember that there's a trick to this, which is if we expect so we essentially have a sequence of, I'm just going to print these just so that I have a sense of them. All right, so the K. Let's just run this real fast. So for instance, that's the simple input. So those are our constraints here that we need to solve for. All right. So now, additionally, do we know that all of these are prime? Let me just take a look at this. 739 is prime, I think. 460. All of these look like they're prime, which also helps. So we know then that this has some property such that it has to occur. What's this value here? 13, 17, 19, 41, 37, 461, 29, 739. Okay, that's a reasonable number. This, I believe, should be a 64-bit number. Yeah. It is, in fact, a... Yep, it's about 50 bits. Okay, great. So, how do we solve this? So, if these were all needing to add precisely to 0, then it would be pretty straightforward. But it's not. So I think we constraint solve a pair of them at a time. And then after that, you can always add the product of all the previous numbers to get the next number. Okay. I think that should be correct here. So let's try this. Okay.
As the longer you do the lower the threshold is.
All right.
Depending on what it is.
Yeah, I'm sure there's a convenient numerical solution to this, but I am pretty sure that this will complete reasonably economically. So,
We're not doing that anymore. We have yeah, when you look at the cost value report, it's going to be
all right.
we did see so when he does that, maybe we can get in some of the big
All right. I think that should do it. Wait, there's a problem here. That needs to happen here. All right. All right, I think that should work. Let's test it on the small input first. 1006. Oh, yep, that's correct. Yep, okay. So I believe that my answer is correct, so I'm just going to pipe it in and see what happens. And that's correct. Rank 147. How? How? Okay. I guess I need to give myself a little bit of credit. I have a little bit more exposure to discrete math than other folks. And I also have been doing these kinds of puzzles for a while. Math camp for the win. So, yeah, okay. That explains how that happened. I was not expecting to get above like the top 200 this year on any puzzle. I am very pleasantly surprised by this. Great. Let's put in a debug flag in case people don't want to see the gory details. Okay. All right. And great. So, and let's print that. Okay. So just to walk people through what I did, since it may seem completely magical, for this example, wait. Oh, I see. We're now we've taken the bus to the airport. We're about to be at the airport again, probably to fly back again to the hub and try again. Okay. So here's what I wind up doing. So we start by noticing that for any given position, there is going to be one example value mod that bus number that equates to 0 or 1 or 2 or whatever, and then once we find an initial number, the second thing that we can do is we can remember that if you multiply that number by 7, it's always going to continue to be congruent to the same thing. So now I can repeatedly multiply this first position, for instance 0, I can repeatedly add 7 until I find something that is equal to that satisfies this t plus 1 is congruent to 0 mod 13. So in this case, the value is 77, which winds up being t plus 1 is 78, which is congruent to 6 mod 13? Yeah, that's right. Or which is 6 times 13. Because I've only been adding 7s, which make this equation still hold true. So now I have something that satisfies 7 and 13. So now, if I add 91s, I'm not going to touch this equation, but I can continue to solve this equation here. And so on, and so on, and so on. The math trick that I was searching for in my head and was like, I'm not sure whether I want to do this, is there is something there is something that does not involve repeatedly adding until you find the right result, because it might take a number of iterations, especially for these kind of larger divisors, like over here, the largest divisor we see is 739. So it might take 739 iterations to find the right thing that is modular, or that is congruent. But on the other hand, 739 iterations is fine, like in computer terms. But if we really had to, we only actually would need to take about log 739, because there is something that's really cool. It is called the Euclidean theorem. So the Euclidean algorithm allows you to calculate congruences and find that number immediately without having to manually step through. So yeah, there's something on the Khan Academy here about the congruence relation. Grumble. It's somewhere over here. Where is it? Yeah, there is a method that the Euclidean algorithm makes possible to quickly find what number it's going to be, because in my code I'm repeatedly adding by the thing that keeps it invariant with regard to the previous ones. So be on the lookout for the Euclidean algorithm, but in this case I didn't need to use it because we were given a number that was not several thousands or millions. Instead, we got at most 739 additions need to happen in here before you're guaranteed to wrap around. This also explains, by the way, why these numbers were suspiciously prime. It turns out that you are not guaranteed to find a value that matches if the numbers are co-prime in any way, if they share common factors. So yeah. There's some fascinating maths going on there, but for these purposes, the only important property you needed to notice was that if you have something where the congruence relation already holds, adding the value k to it any number of times doesn't change the fact that the previous relation is true and allows you to make subsequent relations true. So that's how you make it reasonably performant. Cool. I'm going to go ahead and commit this in case people have questions about it. Feel free to ask me in the chat. Otherwise, thanks for tuning in. And I'm not sure, honestly, how to communicate about this puzzle to other people who are looking to solve it and get a minor hint, because it's very hard to give a minor hint here, right? Like, the only hint I could possibly give someone is going to be a major spoiler, and that's going to be a little bit frustrating. But on the other hand, like, if someone genuinely has never been exposed to this, right, like, they're not going to necessarily figure it out from scratch, from first principles, so you kind of have to do clue them into what's happening with modular arithmetic here. And if someone has seen it before, they should eventually be able to, as I was able to, stumble their way into, wait a second, this doesn't actually require a lot of, Euclidean algorithm. You can make it slightly faster, like, you can make it 5 or 10 times faster, but not, 1,000 times faster that way. Okay. Wait. Okay. Day 13AB solution. And we'll go ahead and push that out. Oops. All right. There we go. All right. So if you're interested in the code, it is github.com/lizthegray/advent-of-code. And I will see you all tomorrow. Same bat time, same bat station. let's go ahead and raid Vincent. And for those of you watching on YouTube, remember, like, subscribe, etc. Cheers.